Welcome to our unit on polygons and quadrilaterals. Today for day one, there is a lot of material. I'm going to split it up into a few shorter videos. That way, when we pause as a class, we can talk about the different concepts that we've talked about. Um, the one thing that I did notice, we started, and I'm not even going to read down that far into the notes, but we talked about this word, and I'm going to highlight it. Let me grab a highlighter real quick. We talked about this word convex polygon, a convex polygon. So what is convex? I want to show you a couple of images before we get started, just because I think it's important that you understand the difference between these two words. And this is where Ms. Valverde can help with the Spanish translation if you need her to. But I think the pictures will take care of it. Okay, so just in a general sense, when you have a concave picture or object versus a convex object, the concave object will curve inward, like this one is doing. If you notice here on the sides, it's curving inward, whereas the convex one is curving outward. And so that's really the difference between concave and convex when you look at a shape. Now, as far as a polygon goes, a geometric shape like a square or a triangle, we've talked about triangles before, or a circle, they're all, well, circles might not so much because they don't have corners. But anything that is like a square or a rectangle or a triangle or a trapezoid, those types of things, those are polygons. You guys might have heard, in Washington, D.C., we have a pentagon. That pentagon shape is a polygon. There are polygons with more than 4 or 5 sides. They're all over the place in real life, really. When we look around, I mean, even if we look at our Chromebooks, those are square or rectangular in shape. Those are polygon shapes. So everywhere we look in real life, there are polygons. We just don't really think of that as being a polygon. So we're going to be investigating shapes today and probably again tomorrow, maybe for a couple of days, that have a different number of sides. Remember, a triangle has 3 sides. But we're going to be learning about shapes that have more than 3 sides. So let me show you briefly, before we go back to the notes, what a convex and a concave polygon might look like. Now, these are just 2 examples, but the one on the left is convex and the one on the right is concave. And I think you can see that the concave one, if you can see my pen a little bit popping in there, it's tilting inward. Can you see that? It's doing it on the other side too. It really doesn't have to do it more than once, but that's what's making it concave. It's kind of caving in. And that's why it is considered concave. Now, geometrically, when we talk about this in a geometry context, we're talking about the size of the angles inside the shape. So when we talk about concave, we're talking about every angle inside is less than 180. But when we talk about concave, you could have at least one that is bigger than 180. And what I'm going to do is I'm going to grab my pen and I'm going to put I'm not saying that concave is bad, but what I am here to tell you is that we are only going to be focusing on the convex polygons. So you don't really have to worry about the concave, but I did just want to give you a little bit. I mean, you guys are bright people. I think it's important for you guys to understand the difference between the two. The convex ones are the ones that we traditionally see more, not just in math, but in real life. So those are the ones that we're going to explore in this unit. Okay, so having said that, talking about interior angles, making sure that we understand that an interior angle means an angle that's inside whatever the polygon is, inside the polygon. I just want to make sure before we go back to the notes that we clear all that up because we are going to be talking about interior angles first. That's our first, job this morning. Okay. So on page 1 of your packet, it says day number 1, interior and exterior angles. In this video, we're going to be talking about interior angles, part 1. So to find the sum of the measures of the interior angles of any convex polygon, let's remember the triangle sum theorem. And you might go, did we learn a triangle sum theorem? You did, but we probably didn't call it a theorem, but it is. It's a geometric theorem. We learned about it when we talked about how many degrees does all 3 angles in a triangle add up to. And hopefully in your brain, you are thinking 180, but it wouldn't surprise me if some of you were thinking 360 because we just finished circles. But remember, we're talking about a triangle here. So the triangle has 180 degrees. Okay. Now let's move and use that information. Let's talk about a quadrilateral. Now here's where some of your English class, and I know you guys are thinking, oh boy, here we go. Miss Lucas is trying to put English into the math. But here's that prefix quad. Quad means 4. So a quadrilateral is just a polygon that has 4 sides. Okay, so we're going to draw one. I want you to draw one, even if you don't have the packet on your paper. I'm just going to draw like a terrible rectangle. It's not going to be perfect. It's not going to be beautiful, but it is convex and it does have 4 sides. So we're going to draw a diagonal. And I don't know if you guys have ever seen what a diagonal looks like, but it's going to go from the upper right to the lower left, or the upper left, like I am here, to the lower right. That's a diagonal. It runs diagonally across the shape. So my next question in the notes is, well, how many triangles did you make when you drew that diagonal? Well, I see a triangle here. I'm going to call this triangle number 1. And I see a triangle here. I'll call that triangle number 2. So we have 2 triangles. How many degrees in each one of those? 180. So how many degrees do you have? What is the sum of the measures of the interior angles in a convex quadrilateral? Well, that would be 180 plus 180 is 360. Now you guys might be wondering, that's just like a circle. And you're right. A quadrilateral does have the same number of degrees inside that a circle has. It's kind of cool. All right, so let's try another one. What we're really working toward here, we're not going to do this for every polygon. What we're trying to get to is sort of a rule or a formula that we can use because we don't want to have to draw these shapes every time we need to solve a problem. I mean, maybe drawing the shapes is fun, but it'll get old after a while. Trust me, if you try to draw something with 20 sides, you are not going to be a happy person. So let's do a pentagon. Notice that I have drawn a pentagon for you. And if you're not believing me that it has that's a root of some sort, but I'm not sure what that means, but I'm pretty sure it relates to the number 5. There's 5 sides in this convex polygon. So we're going to draw 2 diagonals, but we're going to start from the same vertex. Remember, the vertex is the corner. So we're going to start from the same corner. So I'm just going to pick a corner. You can pick a different corner, but I'm going to pick this corner right here. There's not any reason why I picked that. I just picked it. Now I'm going to draw. Can I draw from this corner to this corner? I could, but I would just be tracing a side. So how about the next corner? Could I draw from here to here? Well, that worked. That kind of split it up. And then how about to another corner? There's two diagonals. What do you guys think? Do you like my diagonals? Could I draw another one from here to this corner? No, because that would just be tracing that side. So that's not really a diagonal. So I have two diagonals from the same vertex, and we know that pentagons have 5 sides. So how many triangles do you now have? Well, you have one here, you have one here, triangle number 2, and you have one here. So you have 3. And you have 180 degrees in each triangle. So 180. Let's add them all up. What is the sum? Carry the 2, that's going to be a 5. So the more sides I have, the more degrees I have. That's kind of interesting. In fact, it makes sense. The bigger the number of sides are, the more degrees you're going to have, because the more angles you're going to have. All right, so what we're going to do is we're going to put that information in a table. So let's think back. When we had a triangle, we know what a triangle looks like. A triangle is just one triangle. So when we have 3 sides, that's a triangle, and we have one triangle. That's kind of a silly observation. But how about when we did the quadrilateral? How many triangles did we have? Let's go back and look. We had 2. Okay, so I'm going to go write that down. You don't have to keep flipping back and forth if you don't want. I'm just going to do it for us. And we had 2 triangles. And then when we did the pentagon, I believe we had 3 triangles. So the interesting part is if you look at the number of sides and you look at the number of triangles, and then you look at the number of sides for the next one, 4 and 2 and 5 and 3. I'm not sure if you guys are seeing a pattern or not, but what's happening here is that anytime you have a polygon, you have a certain number of triangles, and it's always going to be 2 less than the number of sides. So here I have 4 sides. 4 minus 2 is 2 triangles. Here I have 5 sides. 5 minus 2 is 3 triangles. Or if I had 6, let's say I had 6, then I would have 6 minus 2, and I would have 4 triangles. So for any number of sides, n, I'm going to have n minus 2 triangles. It doesn't matter what n is. It works for any number of sides. And this n means the number of sides in the polygon. And then what did we do? We took the triangle and we said, or the number of triangles, and we added them up. We said 180 times 1 plus 180 plus 180. Sorry, I got the highlighter moving here. So here we added 180 and 180. We could also say that that's 180 times 2. Well, here we said 180 plus 180 plus 180. that could be considered to be 180 times 3. It's just a multiplication problem. So what we do is we take those number of triangles, whatever that number is, and we multiply it by 180. And what this is a formula to help us calculate the sum of the interior angles in any polygon, if you know how many sides there are. N is the number of sides, and I'm going to write that down here. N is the number of sides. Okay, so that's something we will say that, and we will say that, and we will say that, I promise. Okay, so one other little piece of vocabulary is this word regular, and I'm going to highlight it because it's important. We're going to be talking about regular polygons. Regular means that each interior angle is equal. So if you had a triangle, that would be like every angle is 60. You would have 60, 60, 60. All the angles would be the same. So to find the angle, we divide. See what I did here? We divided the sum by the number of sides. Okay? So what I'm going to get you guys to do is pause your video. And then what I want you to try to do, either individually or as a group, and you guys can decide how you want to do that. What I'd like you to do is I would like you to use the formula n minus 2 times 180 to try to fill out the chart, the table. Now, what I'm going to do before we do that, we know what the triangle is. We're going to put that here. We know what the quadrilateral is. That's the one that we did. We know what the pentagon is. We know what those all are. But let's talk about how many sides a hexagon has. And a heptagon and an octagon, that's 8. A nonagon is 9. A decagon is 10. And then a dodecagon is 12. So go ahead, pause your video. See if you can calculate just this first column, n minus 2 times 180. And when we come back, I'll fill them in for you. Okay, so here what we're going to do is we are going to calculate the rest of the table. This is going to give us a little bit of practice with using the formula. Hopefully you guys did okay. So for the hexagon, I'm going to have 6 minus 2 times 180, which is 720. For the heptagon, 7 minus 2 times 180. For the octagon, 8 minus 2 times 180. For the nonagon, 9 minus 2 times 180. For the decagon, and for the dodecagon. Now, probably you did not like this last one called the n slash or n dash gon. And what that just means is for any shape, you're going to use this formula. That's just where you can write the formula. Okay. So, a couple of things to note here. First of all, you do not have to memorize the chart. You can memorize the chart, and I bet after a while, you're probably going to remember this one. right here. By the time we're done with the packet, it's going to be like circles. You're going to remember 360. But you don't have to memorize the chart. In fact, I don't think it's worth memorizing the chart because you see how quickly you can fill it out. If you know the number of sides and you want to know the sum of the interior angles, you can do that with a calculator really, really easily. Okay. Now, how do we find the regular ones? How do we find the regular ones? Well, I'm going to show you one, and then I'm going to ask you to pause the video again. So what you do is exactly what I did here. You take the sum right here, take the sum, and you divide it by the number of sides. So for the triangle, I took the 180 and divided it by 3, and I got 60. Now for the quadrilateral, I'm going to take the sum, but I'm not going to divide by 3 anymore because I have 4 sides in the quadrilateral. So I'm going to divide by 4, and that's going to give me 90. The pentagon, I'm going to do one more, and then I'm going to get you to pause your video. You're going to get 108. So go ahead, pause your video, and don't freak out if you get a decimal. Okay, so I'm going to continue to fill in the chart. You're going to get 120 here. This is where you get a decimal. And I always call this 128.6, but clearly you have to round. I mean, there's no other way to really manage it. And then divided by 8, you're going to get 135. You're going to get 140. You're going to get 144. And you're going to get 150. Now, what's our formula? What does this look like? So it's the sum divided by the number of sides. And what you just calculated was for a regular polygon where every interior angle is the same. This is like an equilateral triangle or a square where all the angles are the same. That's what you just calculated. Okay. So I'm going to get you to go ahead. We're going to turn this video off and come back together in just a couple minutes.